Hello students, today we shall see Taylor's and Maclaurin's theorem for a function of two variables, similar to Taylor's-Maclaurin's theorem for a function of single variable, but only here partial derivatives shall be used. So let us see what is Taylor's theorem for a function of two variables. If f of xy is a function of two variables which possesses continuous partial derivatives of every order n in a neighborhood of a point first bracket a comma b, and if first bracket a plus h comma b plus k be a point of this neighborhood, then there exists a real number theta with 0 less than theta less than 1, that is theta is between 0 and 1, such that f of a plus h comma b plus k, function value at the point a plus h comma b plus k, is equal to f of a comma b, function value at the point a comma b, plus h into partial derivative of f with respect to x at the point a comma b, plus k into partial derivative of y f with respect to y at the point a comma b, plus 1 by 2 factorial h square into partial derivative of f with respect to x two times, that is second order partial derivative of f with respect to x at the point a comma b, plus 2hk twice hk into partial derivative of f with respect to x and y, that is second order partial derivative, mixed second order partial derivative of f with respect to x and y at the point ab. We can denote it by del square f by del x del y. Here you can denote it by del square f by del x square. F suffix x means del f by del x, f suffix y means del f by del y, okay, plus k square into f suffix y square at ab means del square f by del y square, partial derivative of f at the point a comma b, and it is second order with respect to y, plus 1 by 3 factorial partial derivative of f with respect to x three times, that is f suffix x cube at ab, del cube f by del x cube you can denote it, plus 3h square k into f suffix x square y at the point ab means del cube f by del x square del y, that is third order partial derivative, mixed third order partial derivative of f with respect to x two times and with respect to y one time at the point ab, plus 3hk square f suffix x y square at the point ab means third order partial derivative of f with respect to x one time and with respect to y two times. You can denote it by del cube f by del x del y square at the point ab, plus f suffix y cube at ab means third order partial derivative of f at the point ab with respect to y three times, means partial derivative with respect to y three times, that is del cube f by del y cube you can denote it by at the point ab, plus dot 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 similar terms are there. Rn, last term written Rn. What is Rn? Remainder term. Rn means it is 1 by n factorial h to the power n, then partial derivative of f with respect to x n times, that is nth order partial derivative of f with respect to x, f suffix x to the power n, but at the point a plus theta h comma b plus theta k, plus nc1 h to the power n minus 1 k, and then this is f suffix x to the power n minus 1 y at the point a plus theta h b plus theta k, means it is nth order partial derivative with respect to x n minus 1 times and with respect to y one time. So plus then nc2 f suffix x to the power n minus 2 y square means it is nth order partial derivative of f with respect to x n minus 2 times and with respect to y two times at the point a plus theta h comma b plus theta k, plus dot 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 similar terms are there, nc2 nc3 nc4 etc. last ncn means 1, so it is k to the power n last term f suffix y to the power n at the point a plus theta h comma b plus theta k, means nth order partial derivative of y with respect to partial derivative of f with respect to y, n times derivative of f with respect to y, n times. So this is remainder term, is remainder term in Taylor's theorem, also called Lagrange's form of remainder term in Taylor's theorem for a function of two variables. So this is Taylor's theorem for a function of two variables, just statement. Now in particular, if a equal to 0, b equal to 0, means the point we have considered at the beginning is 0, origin, and suppose h is equal to x, k equal to y, then this Taylor's theorem number 1 becomes special case of Taylor's theorem when a0 b0 and h is x, k is y, it is f of x comma y, left side, Then all the derivatives will be at the point 0 0. Previously it was at the point a b initial derivatives, and last term of course in Rn the derivative was at the point a plus theta h b plus theta k. Now it will be at the point theta x and theta y. Okay, let us see. So when a0 b0 and h is x, k is y, the theorem number 1, Taylor's theorem number 1 becomes f of 0 0 plus function value at the point 0 0 plus x into f suffix x plus y into f suffix y, means partial derivative with respect to x, partial derivative with respect to y here at the point 0 0 plus 1 by 2 factorial, then x square f suffix x square plus twice xy f suffix xy plus y square f suffix y square, and these partial derivatives, second order partial derivatives, are all at the point 0 0 plus 1 by 3 factorial x cube f suffix x cube 3x square y f suffix x square y 3xy square f suffix xy square y cube f suffix y cube, and these third order partial derivatives all are at the point 0 0. And note that here x cube, the factor x cube in the left side of the term is equal to suffix of f in the same term. See, 3x square y, here x square y is the factor, and in the suffix of f it is again x square y. Here it is x y square, it is in the suffix also x y square. Here it is y cube, in the suffix also f it is y cube. So similarity is there, you can remember like that. So plus similar terms are there, and then last term is Rn. Here Rn is 1 by n factorial x to the power n, and f suffix x to the power n means nth derivative, nth order partial derivative with respect to x at the point this time theta x theta y, a0 b0 hk x and y, so theta x theta y, and c1 x to the power n minus 1 into y f suffix x to the power n minus 1 y at the point theta x theta y, etc. And last term is y to the power n f suffix y to the power n at the point theta x theta y, means nth order partial derivative with respect to y at the point theta x theta y. So this is particular case of Taylor's theorem, a particular case of Taylor's theorem about the point 0 0, about origin, in the neighborhood of origin, and this is known as Maclaurin's theorem. As in case of function of Maclaurin's theorem of single variable, also we have got similar name, Maclaurin's theorem. It is Maclaurin's theorem for a function of two variables. And now if Rn, remainder term Rn tends to 0 as n tends to infinity, then this number 2, this Maclaurin's theorem number 2 becomes an infinite series, and we have written this is fxy equal to, for first terms are, for second, third, this fourth terms are similar, whatever written here, and only it will be an infinite series now, dot dot dot. So this is known as Maclaurin's expansion of fxy in powers of x and y in an infinite series. Maclaurin's expansion for a function of two variables. Again, if a plus h is x and b plus k is y, so that h is x minus a, k is y minus b, and if Rn tends to 0, remainder term Rn tends to 0 as n tends to infinity, then number 1, Taylor's theorem number 1 becomes whatever we have written here. This will also become this a plus h b plus k is xy. So f of xy equal to, first derivative will be at the point ab plus, instead of h and k we are writing x minus a and y minus b, and fx fy f suffix x f suffix y at the point ab we have written here in short. Here also h square k square replaced by x minus a square y minus b square, and twice hk it was, so it x minus a into y minus b f suffix xy, here f suffix x square f suffix y square, but at the point ab, so we have in short written a suffix in after third bracket at the point ab. All derivatives will be calculated at the point ab. So this is Taylor's expansion of fxy about the point ab, means in the neighborhood of the point ab, when x and y near to ab, this will be valid. So this is Taylor's expansion, and when a and b are 0, in particular this is actually Maclaurin's expansion. So Taylor's Maclaurin's expansion similar, means Maclaurin's is also Taylor's, particular case of Taylor's expansion. Okay, now let us see some examples. Example number 1, expand sin x cos y. It is a function of two variables x and y in powers of x and y up to third degree terms using Maclaurin's expansion. So this time we shall calculate all the partial derivatives at the point 0 0 at the origin. So f of xy is here sin x cos y, sin x cos y. Okay, so f0 0 is sin 0 is 0, that's why 0. Then f suffix x means del f by del x, partial derivative of f with respect to x, keeping y constant. F suffix x means partial derivative with respect to x, keeping y constant. So sin x derivative is cos x, cos y will remain as it is, and at origin when x is 0, y is 0, cos 0 is 1, so we have got 1. Then f suffix y means partial derivative of sin x cos y with respect to y. This time x is constant, so cos y derivative is minus sin y. And when x and y are both 0, sin 0 is 0, you know, so this is 0. Fy 0 0 is 0. Then f suffix xy, mixed second order partial derivative, means you differentiate this fy line with respect to x, you will get f suffix xy, or fx line with respect to y. So let us differentiate this f suffix y with respect to x. So if we differentiate, this sin x will be cos x, and minus sign is already there, so minus cos x sin y. At the point 0 0 or at origin, sin 0 is 0, that's why answer is 0. Then f suffix x square, means fx line, this f suffix x line you differentiate with respect to x, again second order partial derivative with respect to x. So this cos x derivative is minus sin x, we have written here minus sin x, but cos y is constant, so it will remain. When we differentiate with respect to x, y is constant, so it is minus sin x cos y, and sin 0 is 0, so this value of this derivative at 0 0 is 0. Then f suffix y square, means second order partial derivative with respect to y. Here we have fy line. This fy line, if we differentiate again with respect to y, we shall get f suffix y square. So it will be sin y derivative is cos y. So minus will be there, minus sin x cos y, and sin 0 is 0. So this value of this derivative is also 0 at the point 0 0. Then we calculate third order partial derivatives, f suffix x cube, means this f suffix x square, second order derivative with respect to x, we differentiate again with respect to x, we shall get f suffix x cube. So it is sin x derivative is cos x, but y will be constant this time, so minus cos x cos y, and cos 0 is 1, so this third order partial derivative at the point 0 0 with respect to x is minus 1. Then f suffix y cube, means this f suffix y square line, second order derivative with respect to y, we differentiate again with respect to y, we shall get cos y derivative is minus sin y, so this minus will go, it will be sin x cos y, sorry, sin x sin y, cos y derivative is minus sin y, so this minus sign becomes plus, and at 0 0 sin 0 is 0, so again it is 0. Then f suffix x square y, means if we differentiate this fxy line with respect to x, again it will be fx square y. So cos x derivative is minus sin x, means it will be sin x sin y. See, fx square y we have written sin x sin y, and sin 0 is 0, so the answer is 0. Then fxy square, means fxy line we differentiate with respect to y again, okay, it will be sin y derivative is cos y, so minus cos x cos y, see, minus cos x cos y, and cos 0 is 1, so we get minus 1 here. Also, if we differentiate fy square line with respect to x, you will get the same answer. Fy square line with respect to x, see, if sin x is cos x, so minus cos x cos y, yes, same thing. So all these third order partial derivatives are calculated at the point 0 0, and so on, means higher derivatives can be calculated like that. We are asked to give up to third degree terms, that's why up to third order partial derivatives we have calculated. By Maclaurin's expansion, we have fxy equal to, this is Maclaurin's expansion statement, you will write only here to save time, we have written like that, all these derivatives at the point 0 0, after bracket in the suffix 0 0, here also after this third bracket in the suffix 0 0, means derivatives will be calculated at 0 0, and already we have calculated. So values are substituted from this calculated values, just substituted here, and all second order partial derivatives, let us check. Second order partial derivative, this is 0 0, means all these 3 0, so there will be no term in second degree terms 0, and in third degree terms also two third order partial derivatives are 0, and fx cube and fx suffix y xy square, that is minus 1, so two terms will be there with minus 1, okay. And there is a 3 perhaps missed, what is that, this 3, there is a 3x square minus 1, fx y square suffix is minus 1, so this 3 is missed, 3 is given here now, and these two terms are 0, not written. So finally what you get, x minus taken common x cube, and here 3 missed here, so let us give 3 here again, okay. So which is required, expansion up to third degree terms. Then example number 2, expand e to the power x sin y in powers of x and y up to third degree terms, up to third degree terms. So fxy here is e to the power x sin y, so f 0 0 0, sin 0 is 0. Then if we differentiate this e to the power x sin y with respect to x any number of times, e to the power x derivative is e to the power x, and sin y is constant here because when we differentiate with respect to x, y is constant. So fx is e to the power x sin y, fx square is e to the power x sin y, fx cube is also e to the power x sin y, means first derivative, second derivative, third derivative, all are same. So all are 0 at 0 0 because sin y is 0. Now fy, e to the power x sin y, derivative of sin y is cos y. X will be constant when we differentiate with respect to y. So fy, f suffix y is e to the power x cos y, and cos 0 is 1. So e to the power x cos 0 is e to the power 0 into cos 0 means it is 1. Then f suffix y square means this line again we differentiate with respect to y, cos y will be minus sin y, x constant. So it will be again 0 because sin 0 is 0. Then f suffix y cube means e to the power x cos y derivative, cos y derivative, cos y becomes sin y in second derivative, now third derivative, so sin y derivative is again cos y. So again cos 0 is 1, e to the power 0 is 1, so we are getting minus 1. Then f suffix xy, it is e to the power x cos y. How? F suffix y we have e to the power x cos y. If we differentiate it with respect to x again, so e to the power x derivative is e to the power x, it will be f suffix xy. So if f suffix xy is e to the power x cos y, and cos 0 is 1, e to the power 0 is 1, so it is again 1. Then f suffix x square y is e to the power x cos y, because e to the power x derivative is e to the power x. Again if we put 0 0, then we are getting 1. Now f suffix x y square means fxy line. This fxy line you differentiate with respect to y again. Cos y derivative is minus sin y, so it is minus e to the power x sin y, and when x is 0, y is 0, sin 0 is 0, so 0, and so on. So all third order derivatives calculated. Therefore by Maclaurin's expansion we get fxy equal to, this is the formula you have to remember, substituted, and all the values we have substituted. Just first derivative fx fy both are 0, we have already seen. Perhaps fx is 0, sorry, fx is 0 but fy is 1. So here f00 is 0, f suffix x is 0, f suffix y is 1, so just y will be there. So see, y is there, and then 1 by 2 factorial f suffix x square is 0, f suffix y square is also 0. At 0 0 we have seen f suffix y square is 0, f suffix x square is also 0, so only middle term f suffix xy will remain 2xy, and f suffix xy at 0 0 is 1, so substituted. So similarly f suffix y square is, we have seen, 0, so no terms, only one term, plus 1 by 3 factorial. In third order partial derivative also we have seen 2 terms 0 and 2 terms remaining, 1 with f suffix x square y and y cube. F suffix x square y is 1, f suffix y cube is also minus 1, so substitute it here, other 2 terms are 0. So this is our expansion of e to the power x sin y by Maclaurin's expansion in an infinite series in powers of x and y. Now prove that, example 3, sin x sin y equal to xy minus 1 by 6 x cube plus 3x y square cos theta x sin theta y, plus y cube plus 3x square y sin theta x cos theta y, where theta is lying between 0 and 1. So this is actually Maclaurin's theorem applied with n equal to 3, means fourth term is the immediate term, R3 it is. So let us see. fxy is here sin x sin y. At 0 0 value of the function is 0, sin 0 is 0. Then f suffix x means partial derivative with respect to x, y constant. So it is cos x, sin x derivative of cos x. And at 0 0 it is 0 because sin 0 is 0. Then f suffix x square is again cos x becomes sin x. Derivative of cos x is minus sin x. So at 0 0 it is again 0 because sin 0 is 0. F suffix x cube is sin x derivative is cos x. X square, f suffix x square will become f suffix x cube when we differentiate with respect to x again. But sin 0 is 0. So although we don't need the third derivative at 0 0 because third derivative terms are at theta x theta y, later we shall see. Okay, then f suffix y, partial derivative of fx with respect to y, sin y derivative is cos y, see, sin x cos y, but at 0 0 it is 0 because sin 0 is there. Then again differentiate with respect to y, get f suffix y square, it is cos y derivative is minus sin y, but again 0 because sin 0 is 0. Then f suffix y cube means again differentiate this line with respect to y, it will be sin x, sin y will be cos y, and answer is not necessary at 0 0, we shall calculate at theta x theta y. Then f suffix xy means fy line with respect to x, so sin x derivative is cos x, and y constant here if we differentiate with respect to x, so it is cos x cos y. Now we have got a non-zero term, cos 0 is 1. Then f suffix x square y means this line if we differentiate again with respect to x, it will be cos x derivative minus sin x, y constant, so again at origin it is 0, but we don't need derivative at origin for third order derivative. Similarly, f x suffix xy square means fxy line, if we differentiate with respect to y, it will be cos y will become minus sin y. Okay. Therefore, by Maclaurin's theorem, with remainder term after third term, we get a real number theta with 0 less than theta less than 1, such that fxy is f00 and then x fx plus y fy y suffix fy at 00, then 1 by 2 factorial x square f suffix x square plus 2 xy f suffix xy plus y square into y f suffix y square, but at the 00. This derivative should be at 00. Plus 1 by 3 factorial x cube f suffix x cube plus 3x square y f suffix x square y plus 3xy square f suffix xy square plus y cube f suffix y cube. But this third order derivatives not at 00, at theta x theta y, because this is the remainder term. This is the fourth term after third term. So by Maclaurin's theorem we have got this. Now just putting the values of partial derivatives at 00 for first derivative and second derivative, and at theta x theta y for third order derivative, we get this expansion. You just check, get the answer. So whatever given in the question you have got, sin x sin y is equal to this answer. And then example, now let us see some examples on Maclaurin, Taylor's. We have seen so far Maclaurin's. So example 4, find Taylor's expansion of the following expansion up to third degree terms: e to the power x sin y about minus 1 comma pi by 4 and x y square plus cos x y about 1 comma pi by 2. So number 2 will be homework, and number 1 Roman 1 let us do here. So f of xy is e to the power x sin y here, but in this case the point is a comma b point is minus 1 comma pi by 4. Minus 1 comma pi by 4 is the point here. So a is minus 1, b is pi by 4. So all the derivatives will be calculated at a comma b, means at minus 1 comma pi by 4. So f of ab first, f of minus 1 comma pi by 4, put e to the power minus 1 sin pi by 4. E to the power minus 1 by e, and sin pi by 4 is 1 by root 2. So 1 by e root 2. Then f suffix x means derivative of this e to the power x sin y with respect to x, but e to the power x derivative is e to the power x. As many times we differentiate, it will remain same with respect to x, y constant when. So fx, fx square, fx cube, all are e to the power x sin y, e to the power x sin y, and the values of derivatives at minus 1 comma pi by 4 are all same also. 1 by e root 2, 1 by e root 2, 1 by e root 2. Okay. Now f suffix y means derivative of fxy with respect to y. Sin y derivative is cos y with respect to y, and x constant. So we get f suffix y is e to the x cos y, and at the point minus 1 comma pi by 4, here it is cos pi by 4 is again 1 by root 2. So answer is 1 by e root 2. E to the power minus 1 is 1 by e. Now f suffix y square means again differentiate this line with respect to y. Cos y is minus sin y derivative. So sin pi by 4 is again 1 by root 2. So only a minus sign will be there in the front of in the answer. So minus 1 by root 2. Similarly, f suffix y cube is sin y derivative is cos y. Again, if we differentiate, it is x constant. So if we put 1 and minus 1 and pi by 4, we get again minus 1 by e root 2. Then f suffix xy means fy line with respect to x. E to the power x derivative is e to the power x, so it will remain same. E to the power x cos y. Again, value is 1 by e root 2. Then f suffix x square y means fxy line if we differentiate with respect to x again. So it will be e to the power x derivative is e to the power x. So again, value is 1 by e root 2. Same. Then f suffix xy square means this line if we differentiate with respect to fxy line with respect to y. So cos y will be minus sin y. So there is a minus sign in the answer. Others are same. Values are all same numerically. Change of sign only. So and so on. Therefore, by Taylor's expansion of f of xy, this function about the point AB means here minus 1 comma pi by 4 we get. This is the expansion. Taylor's theorem already stated. Expansion. F of xy is this. F of AB plus x minus a fx, y minus b fy, but all these derivatives at the point AB. Then 1 by 2 factorial x minus a square f suffix x square. 2 into x minus a into y minus b f suffix xy plus y minus b square f suffix y square means second order partial derivative. But those derivatives should be at the point AB. Similarly, 1 by 3 factorial x minus a cube f suffix x cube plus 3 and x minus a square y minus b f suffix x square y plus 3 into x minus a y minus b square f suffix x y square plus y minus b cube f suffix y cube. But all these third order partial derivatives should be at the point AB plus dot 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 up to infinity. Now just putting the values of a and b. A is minus 1, b is pi by 4. So x minus a becomes x plus 1 and y minus b becomes y minus pi by 4. Other things remaining same. Instead of point AB, we have written minus 1 pi by 4, and then finally we have substituted the values and got this answer. E to the power x sin y expansion is, first value was f of AB was, we have seen 1 by e root 2 constant term, 1 by e root 2 plus, Then all the derivatives numerical values are 1 by e root 2. So I have taken 1 by e root 2 common, then x plus 1 plus y minus pi by 4, and then 1 by 2 factorial, but 2 factorial is 2, so you have written 1 by e into 2 into root 2 bracket x plus 1 square 2 into x plus 1 y minus pi by 2 minus y minus pi by 4 square plus 1 by 3 factorial e root 2. 1 by e root 2 taken common because all the partial derivatives numerical value was 1 by e root 2, and then plus minus signs are substituted, noting into these answers these signs. Okay, so this is the expansion of given function e to the power x sin y in powers of x plus 1 and y minus pi by 4. So this is Taylor's expansion. And Roman 2 is homework number 5. The last example, let us see. What is that? Expand sin xy in powers of x minus 1 and y minus pi by 2 using Taylor's expansion up to third degree terms. Here function is sin xy and point AB is 1 comma pi by 2. We have to expand in powers of x minus 1 and y minus pi by 2, means x minus a and y minus b in the theory it was. So AB is 1 comma pi by 2. So a is 1, b is pi by 2, means all the derivatives and value of the function at 1 comma pi by 2 shall calculate. So f of ab is sine of pi by 2, f of 1 comma pi by 2, x is 1, y is pi by 2, sine pi by 2 is 1, then f suffix x. Sin xy derivative with respect to x, y constant. So cos xy into y. So y cos xy, because y is constant in this process when we differentiate with respect to x. And so partial at the point 1 comma pi by 2, the value is pi by 2 into cos pi by 2, cos pi by 2 is 0. Then again if we differentiate this f suffix x line, we will get f suffix x square, partial derivative, second order partial derivative with respect to x. So it is again cos xy derivative is minus sin xy and into y. So that's why this becomes y square, minus y square sin xy. And at the point 1 comma pi by 2, the value is minus pi by 2 square sin pi by 2. Sin pi by 2 is 1. So pi square by 4 we are getting with a minus sign. F suffix x cube means this line again if we differentiate third order partial derivative with respect to x. So another sin xy will again become cos xy, but another y will come. So minus y cube cos xy. Cos pi by 2 is 0, that's why this value is 0. Then f suffix y means this fxy sin xy derivative with respect to y, if we differentiate with respect to y partially, then x constant. So it will be x into cos xy. See, x into cos xy. And cos pi by 2 is 0, that's why at the point 1 comma pi by 2 this value is 0. Again if we differentiate with respect to y partially, then we get another x will be coming, cos will become sine with a minus sign. So minus x square sin xy, sin pi by 2 is 1, that's why there is a minus 1 is the answer. X is 1. F suffix y cube means this line again if we differentiate with respect to y, we shall get another x into, so min x cube and sin xy becomes cos xy. Cos pi by 2 is 0, so this value is 0. Then f suffix xy means mixed second order partial derivatives. This fy line let us differentiate with respect to this fy line with respect to x. So here u into b product rule will be there. So x remains, cos xy derivative is minus sin xy, so minus sign is there, sin xy is there, and if we differentiate with respect to x, y is constant, so y will be multiplied. See, there is y, so minus xy sin xy plus cos xy remains, derivative of x with respect to x is 1, so cos xy. Now at the point 1 comma pi by 2, when x is 1, y is pi by 2, so cos pi by 2 is 0 and sin pi by 2 is 1, so we are getting minus pi by 2. Now f suffix x square y, so this line if we again differentiate with respect to x, so here again u into b rule, there is cos xy. So sin xy derivative is again cos xy into y, because we are differentiating with respect to x, so this xy becomes xy square cos xy. Then minus xy remains, sin xy derivative is then sin xy remains minus x into y, so minus x into y derivative with respect to x will be only minus y, so that's why minus y sin xy. And here cos xy another term, so cos xy derivative with respect to x is minus sin xy into y, so that's why this minus y sin xy another term, so that is actually minus 2y sin xy it becomes. So when x is 1, y is pi by 2, we get cos pi by 2 0, sin pi by 2 is 1, so minus 2 into pi by 2 sin pi by 2 means minus pi. Okay, then fxy square means fxy line if we differentiate, this line if we differentiate again with respect to y, so again u into b rule here and cos xy is single term here, so sin xy derivative is cos xy into x, because this time we are differentiating with respect to y, so another x will be here, so that's why it is minus x square y cos xy. Then sin xy remains, this minus xy if we differentiate with respect to y, we shall get only minus x, that's why minus x sin xy. Now this cos xy term if we differentiate with respect to y, so it will be minus sin xy into x, that's why minus x sin xy. So another, it is becomes minus 2x sin xy. When x is 1, y is pi by 2, we get cos pi by 2 is 0, and x means 1, y is pi by 2, and minus 2, x is 1, y is pi by 2, so sin pi by 2, sin pi by 2 is 1, that's 1 minus 2. So got. Therefore, by Taylor's expansion in powers of x minus a means x minus 1, y minus b means y minus pi by 2, we get f of x y equal to, this is the formula we have written, Taylor's expansion formula. Only instead of ab directly we have written 1 and pi by 2, f of 1 comma pi by 2, x minus 1 into f suffix x plus y minus pi by 2 into f suffix y, but this partial derivative should be at the point 1 comma pi by 2. Then 1 by 2 factorial x minus 1 square f suffix x square plus 2x minus 1 into y minus pi by 2 into f suffix xy plus y minus pi by 2 square f suffix y square. These partial derivatives, second order partial derivatives at the point 1 comma pi by 2. Then 1 by 3 factorial x minus 1 cube f suffix x cube plus 3 into x minus 1 square y minus pi by 2 square f suffix x square y plus 3 into x minus 1 y minus pi by 2 square f suffix xy square plus y minus pi by 2 cube f suffix y cube. All these third order partial derivatives should be at the point 1 comma pi by 2. Now putting the values of partial derivatives calculated above, we get this is the expansion, and some simplification we have done also here. These first order partial derivatives are 0, so no term here, and second order 3 terms are there, and for third order first fx cube and fy cube, the derivatives are also 0, already we have seen 0, fx cube at 1 comma pi by 2 0, fy cube 0, other terms are there, fx square y fxy square terms are already there with minus pi value and minus 2 value, so these values are substituted, and then this is the expansion, which is required expansion of sin xy in powers of x minus 1 and y minus pi by 2 in Taylor series or Taylor's expansion. So thank you for today.